Welcome back to ViViMaT, the PhD sessions. We now discuss submarines and AFMs with Brandon McClimon and how apricot dumplings turn into hot dogs with Tobias Brink. Coatings is a peer-reviewed journal of coatings and surface engineering published online by MDPI on a monthly basis. All right. So I have some questions for Brandon. Is that cool with you? And I do not just want to know your favorite ice cream, but also your favorite submarine, please.
Well, my favorite ice cream is black raspberry chocolate chip by a company called Graders in Cincinnati. And my favorite submarine, I guess, would be my submarine, the USS Asheville, which was based in San Diego, and that was in Guam. What's that?
No, just okay. So that was the name of it. Okay, cool. I didn't read in your CV. The only one I've ever been on is the Nautilus in Groton, Connecticut. But that's just a museum, of course.
I've actually never been on it, even though I lived in Groton for 3 months. So
really, how can you not go? Well, I guess you've been on a submarine so much.
At that point. So.
Okay, so the first thing I noted is that you actually mentioned Mark Robbins twice. I don't know if that was on purpose or if he's really so important for your work that you had to mention him, either as a nod or not. You had to mention him anyway, right?
Mm-hmm.
Were you involved in any of the?
Were
you involved in any of the papers in his in memoriam section or?
I wasn't actually, although having read some of the issue, one of the first half of my talk, that paper might have fit in well there. Although, I mean, I rely on his work in a sort of hand-wavy way in a lot of places, and I think a lot of those papers were able to much more concretely examine his stuff. But yeah, he's been important to my research for a long time. My boss, Rob Karpik, he's always been very good friends with him, so he came and gave a couple talks to our group over the years, but just serendipitously, the work I do relies heavily on, a lot of his work, at least the stuff I've worked with is, or looked at is, looking at contact mechanics at these small length scales. And that's just really, really important to what we do with the AFM in our group. So it just comes up over and over, and he produces a lot of nice tools for experimentalists to use, So late in my talk, I rely on, at one point, he had a paper talking about when if you have a rough sphere sliding on a surface, there's actually a transition pressure where you go from, this multi-asperity contact till all the asperities get compressed down and you end up with Hertz again. And so tools like that that can be provided to experimentalists where you have parameters you can measure just end up being really invaluable. So over and over, it seems like I've relied on his work even before the sad news last year.
How about then I flip my questions that I was going to ask you, and I start with the one that actually pertains to that. So what you do is that you take the friction force versus the load behavior, and you extrapolate your measurements or the results of your measurements, and you extrapolate that to that critical load that you get from considerations that Mark put down. I think it was Mark and Lars, right?
That's right.
Yeah. And so now it looks like a pretty long stretch, huh? Because let's say here you have your data, and here at the 20 micronewtons is that boundary, and there's lots of dotted line in between, or even, like this sublinear with the 0.52 exponent.
Absolutely.
So let's just imagine that you had to put error bars on that somehow. I guess you mold it over in your mind a little bit, but you put down like 80% of a reduction. Is that what's the range in that? How big is the error bar at the very end of that extrapolation range? That's what interested me.
It is large, that error bar. So for instance, I'm extrapolating from, I think it's less than 10% of the overall length is the actual experimental data. So I'm extrapolating a long way. And not only that, I'm doing it with a lot of uncertainty in the contact geometry. And actually, I have something for this. So if I'll just share my screen for a moment. Oh, can I share my screen?
Yeah, I think Carsten needs to allow you, but he's the boss. He's the boss. Can you make Brandon either a presenter or? Yeah, at least I got a message that it should work.
Yeah. So if you look at this figure here, so I show this in the talk, but what I don't show in the talk is if you look at this this AFM image of the tribofilm, the Hertzian area of contact is represented by this green circle here in the middle of the tribofilm. So what's actually happening is that the size of the tribofilm greatly expands beyond the Hertzian contact radius. So when I do that extrapolation, I'm actually, for the single asperity case, I'm using a vastly underestimated real area of contact because the squishy tribofilm expands far beyond the Hertzian radius. So that would argue for a much larger reduction in the interfacial shear strength. But then going against that is the fact that, you know, I extrapolate using the scaling exponent that how do I unshare? Yeah, so I extrapolate using a scaling exponent of 0.52, whereas if it were a true Hertzian case, you would expect it to be 0.66. So if I were to just impose the scaling exponent for a single asperity contact as opposed to this intermediate value between a Hertzian contact and a punch probe, it would end up being more like 50% reduction in interfacial shear strength. So I think overall it's very difficult to say with a lot of certainty, you know, how large the uncertainty is in that extrapolation. I mean, what we can say pretty with a lot of surety is that there's a large reduction in the interfacial shear strength.
Well, just by the fact that it's sublinear and that it curves down, so there has to be a reduction. It's just a matter of, you know, if you can really say that it's that those 80%. I mean, it might even be more. Who knows? But
yeah. So it could go either way. But I would say, you know, probably that could be off by as much as 50%, 30 to 50%.
All right. Well, that was, you know, a good and graphic question. Actually, answer. Sorry. I suggest that Carsten does another one so other people also get a chance. And I think you need to unshare somehow.
Yeah, I'm trying to figure out how to do it.
No, I cannot unshare that because if I unshare, then I have to dismiss Brandon from the chat,
no.
and Brandon has to unshare himself.
Okay.
He must
Oh wait, I
stop
found
the
it.
sharing.
Okay.
Got it. We're good. We're good. Sweet.
It's
So,
working.
Carsten,
It's working. I tried it last time and I kicked somebody out from the lecture. Yeah, thanks. Very nice work, by the way, Brandon. I also want to know a little bit more about the submarines later on. We should actually turn to Tobias because Tobias has such a very professional equipment in the background, and we skipped him now for 46 minutes already. What a shame. So Tobias, first of all, you know, it comes the ice cream question. So ice cream, please.
Lemon.
Lemon. Very good, very good. So now turning from lemon to something that actually is a question from Stefan, but I will just rob his question now.
You're taking my questions?
Yeah, I'm taking your questions because you were laid back now with Tobias and I will start asking him something. So Tobias, how do you account for the volume of the initially placed rigid particles in your wear volume consideration? Or is your wear volume basically defined as the increase of that volume? That was one of Stefan's favorite incredible questions for today.
That's an easy one. We excluded the initial volume.
I expected, yeah. That's the easy one because that's the only thing that Stefan can deliver. No, sorry, Stefan.
That was just to check if you were listening, Tobias. I have much better questions for you.
You can do some much better questions later on, and then we will check. Okay, so you answered that already? That's it?
Well, I mean, there's in the end, because the initial volume you put in, it's kind of arbitrary, right? You don't learn anything physical from that. So what you want to know is how the particles grow. So you kind of exclude that.
Okay. Then I have to, Stefan, I'm sorry. I have to read another one to see if this is more difficult now to Tobias. You said, Stefan, in your 3D, 3-body MD simulations, Stefan called that apricot dumplings. Okay. Did you ever manage to obtain a rationalization of when the interlocking starts producing the adhesive bridges that lead to much higher friction? Sounds more complicated, but maybe the answer is also quick and dirty.
Yeah, the answer is for sure dirty because there's really no rationalization. It's a stochastic process. So what you have is you have a bunch of cylinders rolling around the surface, and they have to touch. Then they can kind of stick together. Especially in this simulation, there's no passivating oxygen or anything like this in the simulation, which in reality would probably be different. So you would not stick as closely, perhaps, depending on the conditions. But here they really like to stick together if they touch. But when they touch, that really depends on the surface roughness and all of these things, because these particles, they don't roll completely regularly, but they might encounter an obstacle, and they might change direction a little bit, and so you introduce some randomness, and at some point they start touching. And if you do that probably with a large sample, you might perhaps get some trends, but this is not possible in MD. You need probably super large surfaces, a lot of particles. It will probably depend on the density of the particles you have. So if you have very few, they will not be coming close. If you have a lot of them, they will touch almost immediately. So this is, one would really need some sort of more continuum-like approach to follow these particles, which is also too hard to do at the moment, I guess, because the interactions are really complicated. They form adhesive bonds. It's quite hard to make some sort of coarse-grained model of this. So there's really no good rationalization when they start doing this.
Okay,
Okay.
Stefan.
It makes perfect sense. And I think the number of your rigid seeds is something of the order of 12 or 16 or something of that type. Yeah. So of course you can't do statistics with that. If you had at least 100, you could check, okay, because I think it really looks like first you're doing apricot dumplings and then they become hot dogs, right? It looks like hot dogs at the Quickie Mart, and then at some point the hot dogs start sticking to each other, right? And then they interlock and can't roll anymore, and then basically you go from rolling to a plowing sort of thing, right?
Yeah, it's not really
call it that.
Well, we called it like shearing rather.
Yeah.
Because they stick, and because these seeds, they are rigid, but they are kind of coated by enough material that it's not really rigid or abrasive particles in this case. So it's more of a shearing. And we also saw basically we had the comparable setup. So we tried different initial particle shapes, all of this stuff. But the behavior is equivalent, but when they stick together is random. So you see basically the same rolling behavior and suddenly it sticks together. And the sliding distance for that is completely different.
Mm-hmm. Your particle shape is cubo-octahedra, right? Something like that.
It's some sort of complicated polyhedron we chose randomly. And then we didn't look further because it doesn't matter. They're coated almost immediately. So they're in the end, they're round. Actually,
since the evening is progressing and the Euro Cup is starting soon, I'm going to give you a choice. So I have one question that pertains to the fitting of the wear volume and your fit parameter K prime, and I have another one that is about the curvature of the wear rate over load. Which one would you prefer to talk about?
Let's go with the second one. We didn't do
the curvature
stuff, yeah.
Okay, so this is about mesoscopic modeling. So I don't know the first thing about mesoscopic modeling, but you claimed that the softest material that you have in there, you don't only claim, you can see it, that if you look at the curvature of the wear rate over load, if you look at the low load end, you see that it actually curves up instead of down, yeah? Whereas all the higher load, the harder materials, they seem to, from the beginning, curve down, yeah? So that, with negative curvature. So I was wondering, is there a smooth transition if you increase the hardness? Do you get a smooth transition in that occurrence of an inflection point? Or can you talk a little bit, or have you studied this? Can you say a little bit more about that? Is this something that's obvious, or did that surprise you as well?
So maybe I should share the screen so people have a chance to understand what we're talking about.
Yeah, that would be great.
Just a second, I will do this.
Now he was just checking if Carsten was paying attention.
Yeah. I'm here. I'm listening.
Yeah, that's good. So should work now.
So, Tobias, Feuer frei. Yeah.
Share. I think it's this one, right? So we're talking about this graph here.
Exactly. And you can see that let's say 3 of them seem to have negative curvature all over the place, and the orange one has an inflection point at about, I don't know, 0.7 or something. And I was wondering if this is something obvious or if there's something special going on here.
I think there's almost nothing obvious about these sort of things, because I mean it's the sort of thing we don't really. Yeah, but I mean we have experimental data of this sort, but simulation-wise we don't really have this sort of model where we go from a basic mechanism and try to connect it to a macroscopic property. Usually there's no fit parameters here, which is the novelty of that thing. What makes it kind of obvious is that it has to be low at low loads, or it has to be 0 at low loads, because basically all of this is based on this critical length scale. And the important thing is the size of a contact you need to form a wear particle gets much, much bigger the softer the material is. So if you now imagine 2 surfaces in contact, you would, and you have a very low load, you would expect to only have very small contacts. And I think I showed this also on this slide, no, maybe here. So if you look at actually the number of wear particles, you can have basically none. If all your contacts are very small, our models predict and at the microscopic scale that you just can't form a wear particle. And so if your material gets soft enough and your load is low enough, you just can't form a particle. But as soon as you can, it picks up. So I'm not sure if inflection point is really the word. It's just going from low wear to actually mild wear here. And we did not study, I mean, this looks quite simple, but these are all like, yeah, literally thousands of simulations with a very simple model to be able to do that. So this is basically the amount of parameters we could study. There are way more parameters you would actually want to vary. So we didn't really study anything in between the, let's say, the orange one and this yellow one. But what I would expect also is that if you zoom in the low load regime, you would always see something like this, where you have basically a contact map where the contacts are going to be too small. But it might be that the load is very, very small.
Okay, so that would have been something that I thought may happen, that the other curves are, let's say, the way they look is actually more similar, but that that positive curvature part is just so small and really compressed down near the origin. Yeah, that might be. Yeah.
But you also, from a sort of, if you start thinking about lubrication, so in this model we are thinking really, let's say, a strong adhesion between the bodies. But if you start thinking about lubrication, basically you're making the strength of the junction weaker. Like you make the junctions weaker. So you would actually also go, by lubricating, going up here. But if you lubricate a material, obviously your wear does not go up. So kind of the way we think, I mean, obviously this model is very crude. But if you want to include it in the model, what you do when you lubricate is you push this onset here to the right, is a bit the idea we had.
Mm-hmm.
So you make it harder to form any wear particles at all if you lubricate it. So that was a bit our idea, but that has to be really refined a bit more, I guess.
That's cool. Well, this paper here is very recent, so I guess you know what to do. Well, thank you very much. I don't think we have time for much more discussion now, because there's so many things that we need to ask the other people as well. Thank you very much. Yeah, thanks for unsharing. Thanks for sharing and unsharing. All right. Yeah, Brandon, second round. So this is about your microscale experiments, okay? And you show the coefficient of friction as first it goes up by about, I don't know, 50% or something, sort of like this. And then you have that sudden drop. First, you show an overall picture of the entire experiment, and it seems very sudden. And then you zoom in onto that 200 to 300 cycles range where you can see a little bit better what's going on. Now, my question is about the time after that happens. So these 200 to 300 cycles, is that pretty much reproducible, or what does that depend on? And could you tell in advance when it's going to happen, or do you only know that it's going to happen and it's rather stochastic when that drop will actually set in?
Well, it's the latter, but I think we ran into difficulty in that totally reproducing all the initial conditions was challenging because the colloids that we were using were actually these steel colloids that are made for sandblasting. And so the apex radius actually tended to vary quite a bit. So I mean, the one I show in the presentation was really perfect. You know, it was exactly the apex radius matched the radius of the overall ball. And so I had some experiments where it was much sharper on top, and in that case, it actually took a lot longer to induce the initial friction drop. And so, you know, I don't think we know whether it's truly stochastic or if we can actually match it, just because we had difficulty matching the initial conditions as well as we would like.
But it's not like you have dozens of experiments so that you can really get an error bar. So these experiments are so difficult that you call yourself lucky if you can get one really good one, right?
Yeah, so I mean, we have a few, and we grew the tribofilms a few times. But to give one example, I had one where the radius, instead of being 50 microns, was about 500 nanometers. And in that case, the friction started dropping at cycle 1000, but it didn't really crash until cycle 4000. So there was a long period of instability that we chalk up to, you know, the contact pressures were too high at that point to have a really stable film. This is a common thing at macro scale, is that the tribofilm sometimes doesn't stick well depending on what your counterface is.
Yeah, makes sense. So maybe, yeah, the last one is actually probably quite a simple one. At least that's how I imagine it to be simple. So you're talking about a considerable increase in contact area. So there's a couple of things that are counteracting each other, sort of, or seemingly counteracting each other. But would you say that so it's basically just a more conformal contact that you have when you're reciprocating? When you're reciprocating, basically, would you say the contact is getting more and more conformal, and that gives you this much increased contact area, or is it more about film growth? Can you say a little bit more about that?
Yeah, so I mean, I don't think it's just a matter of that you have this, you know, let's say it's 20 nanometers thick, and it's equally 20 nanometers thick everywhere across the contact. I think there's an effect where you're filling in, you know, you form a little bit of tribofilm, and it ends up in the gaps between the asperities. I think that's the only way to explain this, you know, orders of magnitude increase in the real area of contact, is that you're kind of filling in the space between the asperities to go, you know, within 20 cycles or so from an extremely multi-asperity contact to one that's, you know, really a single asperity. But basically in the end, I think it becomes a very conformal contact, so conformal in fact that, you know, it actually departs from the Hertzian geometry and becomes more like a punch. As you can see from the scaling exponent dropping off from 2/3 to more like a half, in that you know, it fills in the space and even gets thicker at the edges to get sort of flat. Okay,
now that's pretty cool. As a simulation person, I'm always impressed with what can be done with experiments if you know what you're doing.
Yeah. No, sometimes I wish the simulations were able to go to the timescales that we need for these experiments. Yeah, it's tricky to match.
I don't want to burst your bubble, but well, thank you very much.